this video is going to be on our next topic on standard enthalpies of formation. At this point, we've talked about enthalpy, calorimetry, and how to calculate changes in energy using calorimetry. We also looked at another method using Hess's law to calculate enthalpy. We looked at molar enthalpies, and finally, standard enthalpy formation is another way to calculate enthalpy changes. Okay, so again, summarized here, we have seen, right, we talked about calorimetry and enthalpy. Okay, we've just finished talking about Hess's law. Bond energies we still have to do. We have talked about molar enthalpy, right? So we've practiced this. We should practice it some more, but we've talked about that. And today we're going to do this. Okay, so let's continue. A standard enthalpy formation, the word standard, we should talk about that first. Word standard means something. It means that it is the amount of energy required to create, so the formation of something at a certain standard. And that standard is a set of conditions, right, 25 degrees Celsius and 100 kilopascals. Now, this has been experimented and repeated and verified, and tables have been created with all of this data for the heats of formation of different substances. And it is exactly that. So it's a measure of energy at a standard condition, 25 degrees Celsius, 100 kilopascals, to make it all uniform throughout standard. Similar to what we've seen, what you saw in grade 11 with STP, right, or SATP. So for those same reasons, it's been standardized, right? So some science here. Delta is change in energy. The lowercase f refers to the formation of the elements of the substances that this value is referring to, and that little degree sign there just means that it is at a standard state. Again, 25 degrees Celsius and 100 kilopascals. Okay, previously we looked at Hess's law, right? So that just took the individual measures of these enthalpies of all of the intermediate reactions, you add them all together, and you get the overall enthalpy of the reaction, right, from A to B. It going then through X and through Y and going to B. The sum of all of the individual enthalpies equals that. So that's Hess's law, and that can be a bit of work, as we've seen. All right, in this much faster way of calculating enthalpy, more efficient way of calculating enthalpy, all you're using is tabulated results, and in a nutshell, it is the sum, including moles, so it is the sum of all of the products, enthalpies of formation, standard enthalpies of formation, subtracted by the sum of all of the standard heats of formation of your reactants, considering moles as well, and we'll do a few examples now. Okay, so this is a table that I'll probably post on a quiz or test that you'll have access to. Of course, you have this table. You will not have to memorize any heats of formation. Right, so you'll have access to these numbers. I'll either build it into questions or you'll be able to see this table. Okay, so notice just one thing here. Wanted to point out that it is in kilojoules. So liquid water. To make liquid water, you need, it's an exothermic reaction, 286 kilojoules, and this is important too, per mole, right? We know that negative sign there means the -1 exponent means 1 over, so it's per mole. So you need that much in kilojoules per mole to produce water, 1 mole of it. Okay. Example. Just looking ahead, I'm going to get another program open while we continue. Okay, so this question, our first prep example is, this involves this reaction, a general reaction, A plus B produces C. So it's asking us for the standard enthalpy formation of our product C. Given that to produce A, it requires that much energy, to produce B, it expends that much energy, and the heat of formation to create C requires this. Okay, we need all of this information, right? And you'll be given this in any question. Now, to follow along or to continue with that formula, we then have to write all of this out. So right here is that formula. So the number of moles of your heat of formation of C, right, because it's products minus reactants. There are no other products. We don't have to add anything else, minus the sum of all of your reactants. So again, here is A, heat of formation of A. Here is B, heat of formation of B. And then we have to include this mole because it represents the number of moles per heat of formation, per substance. So notice that this is a one-to-one equation, right? All balanced here, right? If it weren't, we would have to include those different coefficients wherever you see n. And all we do now is plug things in like you would have done in grade 8 or grade 9. Right, so this is the heat of formation of C, right? Then a sum of all of your reactants heat of formations. Notice that the number of moles cancels out, cancel here, cancel there, and so forth. And you end up with your answer, right? 346 kilojoules is required to make C from this reaction, determining through your heats of formation. Not too bad. Pretty simple. We'll do another example in just a bit. But before we do, wanted to talk about this. We see that different elements, specifically elements and substances found in their natural state, they don't require energy to change, right? They exist as is. So the enthalpy of formation of these substances is just zero. So for example, magnesium or anything elemental that just exists as is, has a heat of formation of zero. There is more detail to this, of course. I'm not explaining. I'll mention just briefly a bit of it here. Now, typically, elements can exist in different states, different phases. So, for example, carbon can exist as graphite, or it can exist as diamonds. Now, typically, you'll go with what you'll find in tables is reference to the more stable form, and that would be, well, arguably can be either, but in this case it's chosen that graphite is going to be the standard reference and it's going to have a zero heat of formation. When looking at phosphorus, phosphorus is going to be zero as well, but phosphorus is interesting. It can exist as different forms. In this case, white phosphorus is chosen, even though red is more stable for different reasons. But essentially, this is just beyond the scope of our course, and I'm just mentioning just to make the point that, again, anything that exists in its natural form has a heat of formation of zero. Okay, so if something is missing in a question, if a value is missing in a question, it refers to, let's say, hydrogen gas, and it doesn't give you heat of formation. Where is that heat of formation? Well, you know that this is a diatomic substance and that exists naturally, so it's going to be 0 kilojoules per mole. Okay. Not too important here. I kept it. I was debating whether I should keep this slide or not, but I kept it because it shows you how much easier, well, you'll see yourself in the examples that are to come, but it explains what we would need to do if we didn't know how to use heat of formation to solve for problems. We would need to find the series of reactions required to achieve the target, right? Then we'd have to use Hess's law to manipulate it, as we've seen algebraically, to cancel things out, research the appropriate heats of reaction of each of the intermediate steps, because they may not always be given to us, right? As they have been in your regular homework questions. Then you'll be able to find the answer. So it would be quite a bit of work. We don't have to do this, of course, in a question. If you're asked to, you certainly will. But I just wanted to point out that there is a better solution or a better method, and this is it. Easier method is certainly this, right? So let's move on to our first example. Okay, so here we have a typical example. Here we have sodium chlorate reacts to produce sodium chloride and oxygen gas in a 2:2:3 ratio. Okay, here are the heat of formation provided to you. Remember, oxygen diatomic, right? It's going to be 0. Remember to know why that is. Okay, now all we do, here's our formula. Heat of formation of your products, the sum of minus heat of formation of your reactants, right? Take into consideration also their moles. Keep your units. You'll see it'll be a great self-check as you go along. So here we are. We have, from our balanced equation, 2 moles of sodium chloride. Remember, it is products minus reactants. So 2 moles of the heat of formation of sodium chloride, 3 of oxygen, but of course that's 0, but I'm just writing it because we need to, minus then your product, right? 2 moles of sodium chlorate. Okay, plug in your values like you did in grade 9. Plug them all in. You'll notice that mole cancels out, right? This is on the outside here, so mole cancels out. 2 moles here, mole cancels out, and you do a little bit of some calculations in your calculator, some pretty simple math there, and we get minus 104.6 kilojoules is your answer, and you're set. That's essentially it, right? Typically These questions are done pretty well, pretty easily. The only common mistake here you need to point out is that the step that is often forgotten is this one. Sometimes students forget to put the correct number of moles next to the heat of formation. That typically seems, if there's going to be a mistake, that typically seems to be the one that is made. Okay, next. Now this I will do. Now this program can lag a little bit when I'm using my ink tablet here, so instead I'm going to switch. Okay, and here we go. Green, I like yellow. Okay, so let's go back to the question though. All right, so here we need to figure out the heat formation of calcium hydroxide from calcium oxide and water. Okay, so we have calcium oxide plus water. States are important here. That's the other thing. States are important. I should go back. Maybe it's easier if I go through here. Looking at this table, you'll notice that states do matter. So be careful with that. If you're asked to consider one of these substances, make sure that the state matches correct, because you can be talking about liquid or gas and they have different values. Okay, we are here. All right, so calcium oxide and water produces calcium hydroxide. Okay, so that produces calcium hydroxide. When it balances properly, there should be a 2 there. All right, so let's make sure this is balanced. We have 1 calcium on either side, 2 hydrogens, right? And look, we have 2 oxygens. Turns out it'll be pretty simple in this case. It's just a 1:1:1 ratio. Okay, so nothing else to work out here. Now our formula, we have heat of formation, or heat of the reaction, is equal to the number of moles of the enthalpy of products, and this is given to us in the question. Okay, and then the sum of the enthalpy of formation, heat of formation of calcium oxide, considering then also the number of moles. Okay, now we plug things in. There is 1 mole of calcium hydroxide, and that has, from the question, we have these values, kilojoules per mole. Okay, then it's 1 mole, right? 1 mole of calcium oxide, then the value of that, of its enthalpy of formation. Okay, also 1 mole of water and its enthalpy of formation. And squeeze a bracket there. Okay, right, so mole cancels out, mole cancels out, mole cancels out. And we have, with a bit of calculator math here, minus negative 81.93 kilojoules is your answer. Okay, that's it. So that's your home fun. Forward me any questions. Hope this helped.